has come to rise and stand. Take the path that's meant for you. Power waits within your hands. Let the truth come breaking through.
Hello everyone, welcome to the lab explanation video for Lab 1.4, Music Generation with Recurrent Neural Networks and PyTorch. What you just listened to was a piece of music that I generated using a state-of-the-art model for music generation. In this lab, we are going to be learning the foundations for building a model that could generate a piece of music like this by training it on an Irish folk music dataset. To illustrate an example of the kind of music we're going to be generating today, I also prepared another example of music using the lab. It continues for about another 2 minutes, but that shows what kind of music we're going to be generating today. To navigate to this Lab 1.4 we're going to be going through today, you can go to the inspiredk.org website and click on the AI Program Labs button. This will take you to the inspiredk.org GitHub, where you can navigate to the MIT Intro to Deep Learning repository. The lab we are going through today is adopted from the MIT Introduction to Deep Learning course, and I edited it under the MIT license. Once inside the MIT Intro to Deep Learning repository, you can navigate to the Lab 1 folder and the Lab 1.4 Music Generation with RNNs and PyTorch Python notebook. From there, you can click the Run in Google Colab link to go through the lab on a platform called Google Colab, which is hosted by Google, offering high processing GPUs to anybody with a Google account for free. Now, let's dive into the lab, and we're going to start by downloading all of the dependencies that we're going to be needing for the lab. We're going to start by importing PyTorch as well as some of its relevant sublibraries like NN for neural network functionalities and Optim for optimizers in the training process. Then we're going to download the MIT Deep Learning package, which was created by the instructors of the MIT Introduction to Deep Learning course for their labs to abstract away some of the more complex parts of the labs, and so we can focus on the neural network learning. We also import several other different libraries such as NumPy for multidimensional NP arrays, OS for file path joining, Time for timing different tasks, functools to have functions that output other functions, IPython have the songs that we're going to generate played back inside of Google Colab, TQDM for progress bars built into the output, SciPy with the write function to create downloadable music files, and ABCMIDI and Timidity for conversion between text and audio musical formats. Additionally, we're going to make sure that we are using a GPU that will significantly speed up the process of going through the lab and will allow us to work with PyTorch GPU functionalities. The libraries will take about another minute or so to download, so I'd like to go through the MIT Deep Learning package and the several functions it offers us in order to make our lab more easy to go through. We have the load training data function, which downloads all of the ABC format songs that we have, and we have extract song snippet inside of the load training data function to extract only the song parts of our dataset and remove all of the extra data, such as the name of the song. Then we have the save song to ABC, ABC to wave, and play wave files to take our generated music in text format and convert it to a playable file inside of Google Colab. The playSong function combines these three functions in order to perform this task. Finally, we have the playGenerated_song function, which will take our generated text containing the different songs, perform extract song snippet on that generated text to extract only the songs, and then use playSong to see what songs will be able to be played so they can be listened to after generation. Finally, we have the three test batch func types, test batch func shapes, and test batch func next step functions to verify that our batch creation function for training is going to be working properly. Now, all of our dependencies have finished downloading in about 2 minutes and 18 seconds, and we are ready to start working with our dataset. The dataset contains thousands of different Irish folk songs in the ABC notation. Let's look at one of the example songs so that way we can see what it looks like. There are 817 songs in our text, and our first song has the name of Alexander's as well as other information. Then we have the song in ABC format, including different letters from A to G in uppercase and lowercase, as well as special characters such as bars, parentheses, colons, and exclamation marks. Let's convert our ABC notation song into an audio waveform so that way we can listen to it to see what the song sounds like. This will take a few seconds as the conversion between text to music is a little bit computationally intensive, and when using the playSong function, we will be able to have our music file generated. It took 9 seconds, and now we can listen to the song, which is about 1 minute long. That was the first 10 seconds of the song, and it continues like so for the rest of the 55 seconds. Now, let's continue and take all of our songs and join them together separated by 2 new lines or enters to create a single string. Then we are going to use sorted and set to create a unique vocabulary containing all of the unique characters in our dataset. This will be crucial in defining what characters our model will be able to generate, and we can see that in total there are 83 different characters in our dataset. Now we have understood our dataset and found all of the unique characters inside of it. We are ready to process our dataset so we can use it for our learning of the model. First, we are going to create 2 different mappings for the vectorization of our dataset, including the character to index mapping to provide each character in our dataset with a set index, as well as the index to character mapping, providing each index in our generation to be mapped to a character in the ABC notation. Our char to index character to index mapping can be used for converting our inputs to a numeric representation for the model, and the index to character IDX to char can be used when we want to convert our model's generations to a ABC notation for musical generation. Let's look at the first 20 characters inside of our char to index mapping so we can see how these characters are mapped to their indices. We can see that new line is set at an index of 0, space at an index of 1, exclamation mark at an index of 2, and so on for the rest of the different characters. Let's take our character to index mapping and write a vectorized string function so that way we can have an input of a string and convert it to an output all containing numbers. We will use the char to index mapping for every character in our input string and store all of those values in a NumPy array. Let's run the vectorized string function on our entire songs dataset so that way we can have our songs represented in numerical format to be worked with for the rest of the lab. Let's look how the first 10 characters in our song dataset are mapped from characters to indices. And we can see that it started with x:1, new line t:\Alex, and it was mapped to a list containing 10 different integers for each character inside of the dataset. Now, let's create some different training examples and targets using the getBatch function, which will create training and testing batches. This will allow us to have our model output predictions for the next most likely character for our input batch, and then compare the next character that was expected to be outputted from our output batch. we're going to input our vectorized songs, a sequence length, and a batch size, and we're going to find the length of our entire vectorized song string. Then we will choose random indices of our batch size from anywhere inside of our song dataset. We will use these starting indices to create different batches where each sequence in the batch is of sequence length. Our input batch will be for every random index that we selected, sequence length long from that index to the index plus the sequence length. And we will do similarly for the output batch, now adding 1 to the index and 1 to the ending index, so that way we can shift our input by 1 so every character can be mapped to its next most likely character. We're going to create X and Y batch by having the np.reshape function work on our input and output batch, so that way each character in every sequence for each batch is having its own respective location. We're going to generate 2 test batches where each sequence in the batch is of length 10, and we will use the 3 MIT deep learning functions to verify that our function is being created correctly. All of the tests are passed, meaning our function is correctly defined, and we can now use it to have batches for the training process. But first, let's look at an example of a batch of 1 with sequence length 5, so we can see how each input is mapped to its output batch. We can see that at step 0, the input is 0 or new line. The expected output is index 60 or E. The expected output becomes the input in the next step, and the expected output is now a new character of index 82. This continues for all 5 steps, and it illustrates how each input is mapped to its expected output, so that way we can efficiently train our model. We now have an understanding of how to create different batches from our training dataset, and we know what our dataset looks like. So we are ready to create the recurrent neural network model. This is a diagram representing how we're going to be building it, starting with an input character for the entire sequence length of our batch size, and passing it through an embedding layer to get the character embeddings of batch size by embedding size. We then pass these character embeddings through an LSTM or long short-term memory model, which will achieve an output of batch size by LSTM units for the number of neurons in our LSTM. Then we have the dense layer to output our predictions based on this LSTM output, and that will provide us with our logits for a given batch size by vocabulary size, meaning that each input is mapped to a prediction output for the different characters that are most likely next. Let's take this model and define the RNN in code by creating a class called LSTM model based on the nn.module, which will enable us to take PyTorch built-in neural network findings and advance on them to create our LSTM. We first start by defining a variable hidden size, as well as vocabulary size and embedding dimensions. We create the embedding layer using nn.embedding to have the built-in PyTorch embedding layer with an input of vocabulary size and an output of embedding dimensions. Then we use nn.lstm from PyTorch to create our LSTM layer, where long short-term memory is perfect for our task, where we need to remember a lot of previous context from the previous music to incorporate crucial musical elements. Our LSTM is going to be taking an input size of embedding dimensions from the embedding layer and outputting a hidden size output for the number of neurons in our LSTM layer. Finally, we have a linear layer to output all of our predictions, taking an input of all of the neurons and outputting the vocabulary size logits, or predictions of the most likely next character. We can initialize our LSTM hidden layer as all zeros for the correct size on the GPU, so that way we can continuously update our LSTM for every predicted character in our batch. We can also define the forward function to take an input of X, pass it through the embedding layer, and if our hidden state for the LSTM is empty, we can update our hidden state and get an output from the LSTM, and finally we can pass that output through the fully connected linear layer to achieve our final output of all of the predictions of the next character. We can now create the model using our vocabulary size and embedding dimensionality of 256, hidden size of 1024, and batch size of 32. We are creating this as a first step, and later on you will be able to customize all of the different parameters for the model. We're also going to ensure that our model is using a GPU for training, and we will take our LSTM, defining it with all of these hyperparameters we create, and put it on the GPU for faster processing. We can finally print out a summary of our model showing all of the different layers that we're going to have, and it seems like our session has crashed, and Google Colab is saying it has crashed for an unknown reason. The best way to solve this is to go back through and run all of the code blocks quickly. So while I'm going to do that, I'm going to go through a quick review of what we've done so far. We started by downloading all of our dependencies, including PyTorch and the MIT Intro to Deep Learning repository. We then got our dataset of all of the 817 songs and examined an example song. We played that song for the first 10 seconds to illustrate the type of songs we will be generating, and we got the unique vocabulary containing all unique characters in our dataset. We also vectorized our text by converting all of the strings into integers using the character to index and index to character mappings. We saw an illustrated example of this character to index mapping by seeing the first 20 characters and their respective indices. We created the vectorized song strings function in order to have an input string converted to numbers, and we performed that on our entire song dataset. We examined the first 10 characters mapped to integers to see how our mapping is working, and then we created the getBatch function to create input and output batches for our testing and training processes. We saw an example of how the input and output batches are mapped, and then we created our recurrent neural network model based on a diagram including embedding, LSTM, and linear layers. We defined it creating a class of LSTM model, and then we created our model using a GPU with set hyperparameters. We can see that our LSTM is defined with an embedding layer, an LSTM layer, and a fully connected linear layer, starting with an input of vocabulary size and mapping it to an output of vocabulary size for the inputs and outputs. We are now ready to test our RNN model without training by creating an example batch with batch size 32 and sequence length 100. We can take the input and output batches and put them on our GPU, so that way we can work with them in our LSTM and we can see the input and output shapes. When we run this code, we can see the input is of shape 32 by 100, or the batch size by sequence length, and our output prediction is 32 by 100 by 83, providing a prediction of vocabulary size for every character in each sequence for each batch. Let's look at the predictions that we achieved from this untrained model by using a probability distribution to find all of the indices we achieved from the output. This provides us with a large array containing many different numbers that don't mean much, so we can convert all of these indices to characters to see a comparison between the input and the output. When we look at the output, we can see it is extremely nonsensical because our model has not yet been trained. This is why we need to have our training process work with our loss and have a lower loss with a higher prediction accuracy. First, we're going to start by defining our loss function using cross-entropy loss, which is highly efficient, simple, and accurate, making it the best option for our task. We're going to create the compute loss function to compare the difference between our outputs and the expected outputs, and we will first convert both of them to a different shape to be compatible with our cross-entropy loss, and then once they are in a different shape, we will compute their difference with the cross-entropy loss and finally output that loss. Then we can create an example loss for the previous prediction that we had from our RNN, comparing the prediction characters with our expected outputs. We can see that our loss is about 4.41, which is extremely high, meaning we have a very low prediction accuracy. That's why we need to train our model, and we will start by defining the model's parameters. First, we will start by defining our vocabulary size, which is 83, and then we will create the parameters dictionary including the number of training iterations of 5,000, which you can increase to have the training process lengthened, the batch size of 16, sequence length of 100, learning rate of 1e-4 or 0.0001, an embedding dimensionality of 256, and a number of RNN units of 1024. If we experiment with these different parameters, we can see how we can achieve a higher accuracy, and I highly encourage you to experiment with them to see what the best songs you are can generate. Finally, we're also going to create a file to store our model's weights in Google Colab, so that way if training is ever interrupted, we can take the weights from that file and continue to generate music with our model up to that training point. We've defined our hyperparameters, and now we are ready to create our training operation. First, we will start by defining our LSTM model using the vocabulary size, embedding dimensionality, and number of RNN units, and we will also put the model onto our GPU for faster training. We will define our optimizer as Atom, which I found to work best for me, and we will also use the learning rate that we set above. Then we are going to create the train step function and start by setting our model into its training stage, and we will have every step in our training process reset by using the .0 grad on our optimizer to ensure none of the previous steps interfere with the current one. We will get the output from our model by passing the provided input of x to get its predictions, and we will compute the loss using the expected output as well as the output that we got from our model, and we will also perform backpropagation on our loss value by using the .backward method and using the .step function with our optimizer to take the gradient value computed by using .backward to optimize our model towards lower loss and higher accuracy. We will also use our train step function in a loop for all of the possible number of training iterations that we have, also clearing all previous progress bars we may have to track our training process. We also create a history list to store all of the losses for graphing purposes and create a periodic plotter to plot the trend of our loss every 2 seconds. For each training iteration, we get an X and Y batch for our entire vectorized songs using the sequence length and batch size we set. We convert the X and Y batch to numerical representation and put it on the GPU for faster training and get the loss value for the X and Y batch. We add this loss value to our history list and plot the history list, and every 100 iterations, we save the model's weights to our file, so that way if the training is interrupted, our best weights will be saved. Additionally, at the end of the entire training process, we save our model's final weights, which should have the lowest loss, so that way we have the best accuracy when generating music. The training process will take a few minutes, and already, while it is starting, we can see it achieves a loss starting at 4.5 and quickly achieving close to less than 2, optimizing towards a value of 0. While it continues to train for about 3 minutes, I'd like to go through what we've done so far in quick review. We started by downloading all of our dependencies, such as PyTorch, and examining the 817 songs from our dataset of Irish folk music. We played an example song to see what kind of music we will be working with, and then we generated a unique vocabulary containing all of the 83 unique characters in our dataset. We processed the dataset for our task of learning by creating 2 different mappings to map each index to a character and each character to an index, and we created a function that takes an input of string and converts it to a list of indexes and performed that for our entire song dataset. We created a getBatch function to randomly sample from our training dataset for the training process, and we also defined our recurrent neural network model with an embedding, LSTM, and linear layer. We created the class LSTM model to store all of these layers, and we defined our model with some basic hyperparameters. We put it on the GPU for faster processes, and we saw that it had an extremely poor character prediction, which was extremely nonsensical. We decided that we should train the model using a cross-entropy loss, and we saw, for example, with our loss function, that the loss of our untrained model was about 4.4, extremely high and meaning our model definitely needs to be trained. We defined some hyperparameters for our model to be trained with, which I found to work best for me. And we also defined our model and its training process using the atom optimizer and all of the set hyperparameters we had. We can see our model is about 65% of the way through our training process, starting with that loss of 4.4 and quickly optimizing towards 0. It started initially with a very fast descent and then started to oscillate back and forth between a value of about 1.5 and 1.0 because when we have a model, it often has to have a different moving between the loss landscape, causing it to go up and down repeatedly as it gets towards a lower loss. While the model continues training, I will go ahead and explain the generation of music process, including with this diagram. We start with an initial input, which is our starting sequence, and we pass it through our model to get the probability distribution. We take the most likely next character and pass that through our LSTM again, continuously doing this for a given generation length that we want to have. Now our model has almost finished training, quickly getting towards a loss of 0.5. Now that it has finished, we can see it almost achieved a loss of 0.5, meaning it is going to be very accurate in its generation. Let's define this prediction procedure in code using the generateText function. We will take an input of a model, a starting string, and a default generation length of 1000, and we will convert our starting string to an input using the character to index mapping. We will also change the shape of our input so it is compatible with the model, and we will put it on the GPU so that way it can be done with fast processing. We will create an empty list storing all of our generated text, and we will reset the state of our model so that way none of the training processes interfere with our current training. Additionally, we will clear any previous progress bars to track the progress of our generation. We will have our generation length, and for every set character in the generation length, we are going to get the predictions and the hidden state of our model for the input, and we will also get the predictions and have a prediction probability matrix so that way we can find the most likely next character and add it to our text generated. We will also update our input eval so that way we can continuously input it to our model for the training process. Finally, we will output our entire start string along with the text generated so we can listen to some music. Let's run our generateText function with a start string of x, as the start of the ABC notation files is always x. Additionally, we will use a generation initial length of 1000. It quickly generates all of the music, and now we can use a function, including the MIT Deep Learning extract song snippet, to listen to our music. For all of our extracted songs, we loop through each one and provide it with a given index, converting the song to a waveform and ensuring the waveform is valid. We print that we have generated a song, and we display that waveform inside of the console. We also save our song to the Google Colab files folder, where you can download the song if you want to keep it. Let's run this, and we can see that although it found 2 songs, it was unable to generate any when a music format. So let's increase our generation length to 5000 to generate more songs. The process takes a few seconds to generate the text format. Now we can see we are able to generate 8 songs. However, this has still not created any valid songs, so let's increase our generation length to 7000. You will find that this is actually a common occurrence because sometimes the generation text of our model is unable to be correctly formatted. Now we have 13 songs, and we are going to be able to create a waveform from one of our songs. It will take a few seconds as we need some time to be able to generate the songs and format them correctly inside of the console, and as we wait, we can already see that the first song has been generated and it is going to be displayed inside of our console. While the song is generating, I would like to note that when you go through this lab, you should definitely change all of the different hyperparameters like the batch size, sequence length, optimizers, and more to see if you can generate any high-quality songs or even many different songs in a short generation length. It seems like we have been able to generate a few songs through our training process in about 48 seconds, and let's listen to one of our generated songs. That was about halfway through the song, and it continues for another 15 seconds. And I highly encourage you again to experiment and see if you can generate more songs or even higher quality songs than this. I want you to especially think about training epochs, changing the dataset, or the choice of the start string rather than X. To navigate to this lab and experiment with the hyperparameters, go to the inspiredk.org website, click on the AI Program Labs button, and from there, in the inspiredk.org GitHub, navigate through the MIT Intro to Deep Learning repository, the Lab 1 folder, and the Lab 1.4 Music Generation with RNNs and PyTorch IPYNB. You can click on the Running Google Colab link, which will take you to the lab so you can go through it, experiment with hyperparameters, and listen to your very own generated music. Thank you for joining me in this lab explanation video. Goodbye!